this is Mr. T. Today's lesson is on factoring polynomials. In this lesson we're going to be covering several different factoring techniques that are going to be critical for your future success in math. When we talk about factoring, we're talking about breaking an expression into two or more smaller or simpler expressions that if we multiply those simpler expressions together, we get back our original expression. So we're not changing the expression, we're just rewriting it into a different form. This skill is a core skill that's important for you to master. It's used extensively in higher level math, and as we get into our lesson we'll be seeing that it's an important method for solving more complex equations. Earlier in the lesson this unit on polynomials, we talked about multiplying two polynomials together using the distributive property. So when we're factoring, we're doing that process in reverse. So factoring is the inverse of using the distributive property. And again, we're going to explore several different techniques. Our first technique is an important technique which I call GCF factoring. GCF stands for greatest common factor. So we are looking for a single term, a monomial, that will divide evenly into all of the terms of our original polynomial. If we can find a monomial that will divide evenly, we want to factor it out. So to do GCF factoring, we will be looking at our terms. So we have one term, second term, third term, and we're looking at, is there anything that divides evenly into all of those? So we have to look at our coefficients and ask ourselves, is there a number that will divide evenly into those? And for this one, I made the numbers easy. They're all divisible by 5. And then secondly, we have to look at our variable terms. And if all parts of the original polynomial have a variable term, we're going to factor out, and based on the way our exponent rules work, we will always be factoring out the version of the variable with the smallest exponent. So when we are GCF factoring, we will be rewriting our original polynomial into two parts. A part that is the GCF, the greatest common factor, and then what remains after we remove the GCF, or the leftovers. Since this is just after Thanksgiving, many of you have probably been consuming leftovers. So a thing to keep you organized is we have here 3 terms in the original polynomial, so our leftovers will also have the same number of terms, so in this case 3 terms. So again, our GCF, we look at the coefficients and they're all divisible by 5, so we're going to factor out a 5. And our x's, they all have x's, and the lowest exponent is squared. So now we're going to remove that. Removing is division, so we are going to divide each of these terms by our GCF to remove it. So 5 divided by 5 is 1, and here we subtract our exponents, so we get x squared. Negative 15 divided by 5 is negative 3, and x cubed divided by x squared is x, and 25 divided by 5 is 5, and x squared by x squared, they cancel out, so the x is disappeared. And this would be our answer for this problem. Let's look at a second example. So here we need to determine our GCF. So if we look at 24 and 18, we can factor out a 6. And we look at our x's, they both have x's, so we can factor out an x to the first power. And our leftovers, we're going to again divide by 6x. So here I get 4x squared and minus 3. And that's our second example. So that's the basics of our GCF factoring. So let's now move to our next type of factoring, We're going to now be working with quadratic expressions. So quadratic expression has this format: something x squared plus a number times x plus some constant. So ax squared plus bx plus c. And there's different methods for factoring trinomials. We're going to explore three methods today. In this first method we have trinomials. So this is a trinomial having three terms, and our leading coefficient is a 1. In this method we are performing the inverse of FOIL. So let's just perform a FOIL to refresh ourselves how it works. So I wrote out two binomial terms here, and we can multiply those together. So if we do first, that'll be x times x. Now we do O, the outside, so x times n, so that gives us n x. We do our insides, we get m times x, or mx. And we do our last, which in this case would be m times n. We could group those two terms and factor the x, so I want to do that so that we can see our pattern here. So I have m plus n times x plus m times n. So this is our c, and this is our b. So when we go backwards, we will be looking for a pair of numbers, m and n, that are going to go in our factors. And those two numbers have to accomplish two things. They have to multiply together to equal c. So m times n has to equal c. And that same pair of numbers, when we add it together, has to equal b. So let's look at some examples here. I've got three examples here. They're all somewhat similar. So again, I'm looking for a pair of factors that multiply to be 12 and add to be 7. So 3 times 4 is 12, and 3 plus 4 is 7. So that tells us that this factors into x plus 3 times x plus 4. Okay, so that's our factoring. Here I need a pair of numbers. Now this sign goes this, so I need a pair of numbers that multiply to be negative 12. And when I add them, I get a negative 1. Now if we add two numbers together that add up to be a negative, that means the bigger of the two numbers had to be negative. So here we could use 3 times negative 4. That's going to give us negative 12. And if we add 3 plus negative 4, I get my negative 1. So my factors for this one would be x plus 3 and x plus a negative 4 or minus 4. And here, our third example, here I need two numbers that multiply to be positive, so they could either both be positive or both negative. Since they have to add to be a negative number, I'm looking for two negative numbers. So negative 3 times negative 4, and if we add those together, we get the negative 7. So our factor would be x minus 3 and x minus 4. Now I picked some examples here where this number, the C number, was fairly easy to factor, and we could try various combinations in our heads to see if they work. I just want to go through another example. Okay, in this example we have a value of C here which is not easily factorable in our head. We might be able to recognize that it's divisible by 2, but we probably might not stumble on the combinations that add up to be negative 6. So we want to kind of organize our work in a systematic way here to not miss any of the factors. So we're going to generate sets of factors, and we're going to do their sum. Again, we're trying to check, does the sum equal negative 6? And we want to do it systematically. Now we know since this is negative, one of the factors has to be positive and one negative. And when they add up, the bigger number has to be negative so that it'll add up to be a negative number. Now we can always start with 1. 1 is always divisible. So we would have negative 216. So our sum is negative 216, so that doesn't work. 216 is even, so we can divide that by 2. And our other factor is going to be negative 108. When we divide that by 2, that adds up to be negative 106. That doesn't work. Is it divisible by 3? Now you can use a calculator, but if these numbers, if these digits add up to a number divisible by 3, then the whole thing is divisible by 3. So this adds up to 9, which is divisible by 3, so we get negative 72. Again, just use a calculator. Just start dividing by 1, 2, 3, 4. Keep going until we find our answer. So here we get negative 69. That's not negative 6. Check 4. So if we divide by 4, we get negative 54. That adds up to negative 50. Still no good. 5. 5 does not divide. 6 divides into 216 negative 36 times. So that adds up to be negative 30. That's still no good. 7 does not divide. 8 divides in about 27 times, so we get negative 27, so that's negative 19. As you can see, our sums are getting smaller, so we're hopefully approaching our answer. 9 divides into 216 24 times. That's going to be negative, so we get here negative 15. Still not negative 6. 10 does not divide. 11 does not divide. And 12 divides in 18 times, so we get negative 18, so that's negative 6. So that's what we're looking for. So our factors for this then are x plus 12 and x minus 18. Again, just start dividing by 1, 2, 3, 4, 5, 6, 7 on up. Pairwise using a calculator. Add them as you go. As soon as you find your matching number, you can stop. If we get to the point where our numbers start where this number on the left side is bigger than the number on the right, meaning we're starting to repeat, and you did not find a matching pair, then this quadratic would not be factorable, and we would write down that it is prime, meaning it can't be factored. Alright, our next technique is when the leading coefficient of the trinomial is not equal to 1. Now we'll have two methods here, one that works for simple problems and one for more complicated. First, we're going to be looking at our guess and check method. So we're looking for two binomials that when we FOIL them together give us this polynomial. So we know this number times this number, so the two first have to multiply to be the 3. So this is first times first. And we really only have one combination that will work, so one of these has to be 3 and one of them has to be a 1. Let's look at the other end. This is our last times our last. So these two numbers have to multiply to be 8. So they have to multiply to equal 8. And the key part is our middle, when we use FOIL, that's the outsides multiplied together plus the insides. So we have to try various combinations. So we could have here 3, and this could be 1, and then this would be 8. We can try, again, these are going to stay 3 and 1. We could try 8 and 1 that way. We could try 2 and 4. And last combination here would be 4 and 2. So I'm looking for the outsides plus the insides equaling 14. So here the outsides are going to be 24. Plus 2 is 26. That's no good. Here I get the outsides are 3 plus 8. I get 11. That doesn't work. Here my outsides are 3 times 4 is 12. And my insides are 2. That's 14, and that's what we're looking for. So we know that this then had to be, this is our one that works. So this had to be 2 and 4. So our factoring for this again is 3x plus 2 and x plus 4. The guess and check method works pretty well when you have only one combination of numbers that multiplies to be the A. In this case, there are multiple pairs of numbers that can multiply to equal 6. 1 and 6 or 2 and 3. And so we'll have lots of combinations when we match those up with the combinations that multiply to be 4. You might be able to get the correct answer with guess and check, but I'm going to show you another method that is reliable and what I would call deterministic. It comes up with an answer in a step-by-step procedure. I've called it the A times C method because in our first step is we're going to calculate A times C. So in this case we have 6 times 4 is 24. In step 2 we are going to be factoring our A times C. And we need, so we're going to factor A times C, looking for a sum that equals B. So here we need to factor 24 and get a sum that is negative 11. So we have a positive number here, so they have to either both be positive or both be negative. So in this case, since this is negative 11, they both have to be negative, so we can have negative 1 and negative 24. That doesn't add up to negative 11, negative 2 and negative 12, that's negative 14. Negative 3 divides into 24 8 times, that equals negative 11. So this is an important part of our numbers. Now the next couple steps are a little tricky, they're going to seem odd, but if you follow the procedure it'll work, is we need to next rewrite our middle term of our original polynomial. So we're going to rewrite the original polynomial and we're going to split the bx term using our two factors. So we're going to leave our 6x squared, and now we're going to split this into two parts using those terms. So I get negative 3x and minus 8x plus 4. So if we simplify this, we still have our original polynomial so that we haven't changed it. Step 4 is we're going to group the first two terms and second two terms. Now we have to be careful when we group. If we put a parentheses between a term and a negative sign, it changes the value of the polynomial. So I need to write this. I need to put a plus here. Plus negative 8's the same. So now I can group here, and it doesn't change our problem if we factored it. Now that parentheses is between that 3x and the plus. Our fifth step is to GCF factor each group. So here, if I GCF factor here, I can factor out a 3 and an x. And I'm left with 2x minus 1. And I'm going to GCF factor here. They're both divisible by 4. And the important skill here is if this leading coefficient is negative, we're going to factor out a negative, so negative 4. So if I divide negative 8x by negative 4, I get 2x. And positive 4 divided by negative 4 is negative 1. Now in this step, if we've not made any mistakes all the way down here, these two leftovers of the two GCF factorings will be the same. So our last step is to GCF factor our common binomial. And so we are going to factor out the 2x minus 1. Now if I divide that by 2x minus 1, they will cancel out. Whoops, there's no parentheses there. Let me rewrite that and get that correct. So here we have 2x minus 1. And if I factor out here, I'm left with a 3x And here, when I divide that, I'm left with a negative 4. And that is our final answer. If we FOILed this out, we would come up with this polynomial here. Again, these two common factors will be one term, and the part in front of each of those is our second factor. Okay, our next factoring method is difference of two squares. So let's look at here this particular pattern. Let's FOIL that out. So if we FOIL that out, we get a squared times x squared when we do our firsts. Now when we do our outsides, we get negative a times b times x. And when we do our insides here, we get a times b times x. And when we do our last, we get negative b squared. These are the same terms, positive and negative, so they cancel out. So we're left with a squared x squared minus b squared. And this we could rewrite as ax quantity squared minus b squared. So here we have two things that are squared, so those are called squares or perfect squares. And we have a difference, so that's the term. So we're going to be starting with something that looks like this, and when we factor it, we're going to be going this direction. So if we look at some examples of the difference of two squares. Now I'm going to take a step here and show this. So this is x squared minus 2 squared. So that's our pattern here. So using our pattern, this is going to factor into x plus 2 times x minus 2. If we looked at, say, 4x squared minus 9, that's going to be 2x squared minus 3 squared. So that's going to factor into 2x plus 3 and 2x minus 3. So you can see we're taking the square root of our first term, square root of the second term, and putting it in those two square roots into factors, one that's plus and one that's minus. So we'll always have one plus and one minus. This would not be factorable by difference of two squares because 8 is not a perfect square. This is also not factorable. 9 is a perfect square, but 6 is, so that's also prime. And another common mistake is if we had x squared plus 4, that is also not factorable because that's not a difference. And you can try on your own. You could say, well, maybe it's x minus 2 times x minus 2. But if we FOIL that out, we're going to get x squared minus 4x plus 4. That's not the same as this. So a sum of 2 squared is also always prime. So let's wrap this up. Sometimes, as we've just shown, we can do a single factoring and finish, but there will be some problems as we get into more complicated polynomials where we have to use multiple factoring steps. So we're going to have to use sort of combos. We always want to try doing our GCF factoring first to try to simplify our polynomial as much as possible. And then we will look at the leftovers to see if they can be further factored. So if we look at this, we can do GCF factoring here. We can factor out a 2 and an x. And my leftovers here, I'm left with x squared. Here I'm left with x. And here I'm left with negative 6. Now we need to look at our leftovers. Now that's a trinomial with a equals 1. So we need to say, can we find a pair of numbers that multiply to be negative 6 and add to be 3? And that would be 3 and negative 2. So we can factor our leftovers as x plus 3 and x minus 2. Now you need to keep, a common mistake is to drop this GCF here. So that's still part of the problem. If we FOIL that and then distribute the minus 2, we are back to our original problem. So this has 3 factors, not just 2 factors now. Here we can't factor out anything between the 9 and the 4, but they both have an x. So we can GCF factor out an x, and then we're left with 9x squared minus 4. Here we have two terms that are perfect squares and a difference, so we can use what we just did on the last problem with the difference of two squares. So this is going to factor into that, and again this would be our final answer. And our last one, we don't have x's here, and we could factor this as a trinomial with a not equal to 1, but if we factor out the 5 first, we can simplify our problem. We get here negative 5x, and here we have plus 6. This is factoring into negative 3 and negative 2, so we get 5 times x minus 3 and x minus 2. Now we could have done the a not equal to 1 procedure here, the a times c method, but that's going to be a lot more work than we did here. So always try to factor out a GCF first, and then don't forget to factor the leftovers. Okay, as you practice all these various factoring techniques, I wish you good luck.